We started to look at infinite series, and we're going to be doing a lot of that for the rest of the course. We'll eventually get to the series of functions, the so called Taylor expansion, Taylor series. But for now, we need to focus really heavily on sequences and series of real numbers, okay? And we need to ask ourselves, do these sums converge? Sometimes we can tell if they do, and sometimes, well, we can just test, okay? So in this video, we're going to go ahead, as I move my cup, we're going to go ahead and look at uh, a pair of tests. And in this one, we're actually just going to look at what I call the easiest gut reaction here, and that's called the divergence test. So we're going to jump into it. Um, so we're going to start off with a series here, okay? Remember here that a series is built off of a sequence, okay? And we're looking at the sequence of partial sums. But take a look here, okay? We have a series an, summing an, and we want to see if these are true or false, okay? Well, it turns out the first statement A is the actual theorem, okay? This is the actual divergence test. Okay, this is the divergence test, sometimes called the nth term test. Now, it says that if the limit of your sequence, if the limit of the summand does not go to zero, the series diverges. And that, folks, is true, okay? This is a statement of the theorem, okay? So, if we have a gut feeling, whoops, let me go ahead and fix that here. So, as I fix that, if we have a gut feeling that our series diverges, okay, we just go ahead and take the limit of the summands. And basically this says if the limit is not zero, well, we're done. The series diverges, okay? But let's look at that, okay? Does that mean that if the limit of those terms is zero, the sum diverges? Well, the answer is no. As an easy counterexample, let's go back to our favorite friend, the harmonic series, okay? Summing 1 over n, okay? So note that 1 over n does indeed go 0, but the sum diverges, okay? Because this is the harmonic series, the p series with p equals to 1, okay? So just because the terms go to 0 does not necessarily mean that the series converges, okay? So this is something that we got to be very, very careful about, okay? Well, let's look at part C then, okay? If the limit does not exist, the series diverges. Well, not exists means it could probably go wiggle up and down between bigger and bigger numbers, okay? So this is in fact true. Okay, we won't justify that, but again, not zero includes the case, okay? Not zero includes the case does not exist, okay? It just goes back to part A, okay? Now, if the series converges, then the limit is zero. The limit of the terms is zero. Well, we got to think about that one, okay? So if we know that we have a convergent sum, does that mean that the terms go to zero? Well, intuitively, yes, it sort of makes sense, right? We've seen that with the geometric series, right, where our common ratio r is less than 1. We've seen that with some other special ones, maybe like 1 over n squared, okay? Others, 1 over n to the p, where p is bigger than 1. This is in fact true, okay? And this is in fact the contrapositive of the original statement here, okay? For any of you that go into proofwriting classes like Foundations of Mathematics and the like, okay, you'll learn about propositional logic. Okay, so I have if P, then Q. Well, that's equivalent to saying if not Q, then not P. What does that really mean? If the sum converges, then the limit is zero. Okay, so this is true. And I'll provide a little bit of, a sketch for the justification here. Okay, so let's take a look here. All right. So if I want to prove this, okay, or at least convince myself that it is true, okay, well, let's go ahead and take a convergent sum. So I know that if I sum these guys, let's say that this is some sum s, okay, well then how do I extract, say, the nth term? Well, I can just go ahead and look at partial sums, right? And I'm going to be looking at tails, okay? So if that converges, then that means that the sequence of partial sums converges, okay? So say the sum from n equals 1 to k of an is equal to sk. And now look at two successive partial sums, right? Sk plus 1 minus sk. Okay, you can kind of write this out for yourself, but you can see that you just get the next term, but we know that the sum converges, okay? So the idea is that these terms, okay, these get small. Okay. So I'll leave this as a bit of exercise in convincing yourself, okay, that this does hold, okay, that these remainders, okay, these tail partial sums can be made as small as you like, okay. I won't get into the whole epsilon n definition here for limit here, but you can convince yourself that this is true, okay. So if you have a convergent series, okay, then the limit of those terms is 0. Now be careful, okay, because we saw here, okay, that just because the limit of the terms is 0 does not mean that the sum is convergent. Okay, you got to be very careful about that. Okay, this is how a lot of people misuse the theorem. Okay, but if you know that you have a convergent series, then the limit of the terms is 0. You get that for free. If the series is divergent, then the limit of the terms is not 0. Well, we already saw that. Okay, so by this goes back to part B here, right? So let's go ahead and draw an arrow there. Okay, that goes back there because let's think about it. That's false, by the way. Okay, this sum diverges. And of course, 1 over n does go to 0, which is certainly not 0. Now, this one's really important here, okay? The divergence test can be used to determine whether a series converges. This is actually false, okay? This is false. Just because you don't get a result from the divergence test doesn't tell you anything about convergence at all. That's why it's called a divergence test, okay? If you get a result that says, oh, well, the limit is 0, so I guess it converges, well, no, that's not what that means. Okay, the divergence test cannot be used to determine whether a series is convergent. Okay, just that limit is not enough. Okay, if you get a limit of 0, you have to do a bit more work. All right, let's go ahead and keep going here. Let's actually use this test, okay, if we can. And if it's inconclusive, we'll give a reason. So, what does that really mean to actually use a divergence test? Well, let's look at our first sum here. Okay, 3n over 4n plus 1. We're summing from n equals 1 to infinity. Divergence test just says take the limit of the terms, see what happens. Well, let's go ahead and take the limit here. Okay, 3n over 4n plus 1. Remember, we're just taking the limit of the summands. Okay, well, what do we do here? This is just another calc 1 limit, right? It's equal heavy, okay? You can go ahead and divide out a factor of n in both. And in fact, we'll go ahead and do that here. So we have 3 over 4 plus 1 over n. Okay, I just divided top and bottom by an n. Okay, 3n over n is 3. 4n over n is 4. 1 over n is, well, 1 over n. Well, now take a look here. 1 over n goes to 0. Okay, so in limit, this is equal to 3 over 4. But that's not 0. So the sum diverges. See how easy it is, right? If I have a gut feeling that the sum is divergent, we look at the limit of the terms. If they're not 0, okay, we move on. Okay, but if it is 0, we got to do a bit of extra work. Okay, well, what about B here? Well, you might think it looks like A, okay, but there's something different here, right? Look at the summands. N over 5n squared plus 3. Okay, so we're going to take the limit of this guy. But what's the highest power that it appears? Okay, well, it's going to be n squared. So divide the numerator and denominator by n squared, and I'll go ahead and write that out here. So we have n over n squared divided by 5n squared, let's fix that, plus 3 divided by n squared. Okay, so we'll have the limit as n goes to infinity of, well, let's look, 1 over n on top. And on the bottom, okay, we'll get a 5 plus 3 over n squared. Okay, that's just how we divide over a common denominator, right? We just separate. Well, the top, okay, 1 over n goes to 0. 3 over n squared certainly goes to 0. So we'll have 0 plus 5 in the denominator, but on top I have a 0. This limit is 0. Okay, so what happens? We don't know. This is inconclusive. because the limit is 0. Okay? Remember, let's go back to the theorem, okay? Let's go back to the theorem real quick. If the limit is 0, the series converges. That's false. Okay, the limit of these terms is indeed 0, but the series is divergent. Okay, that's the so-called P test. Okay, because we're comparing it against a harmonic series here. Okay, a certain class of sequence series here. So be very careful. Well, how about this one here? 1 over 3 plus 5 to the n. Well, let's go ahead and just take the limit, right? So we take the limit here of the summands, and this one's pretty nice, right? Okay, you can think about this as, say, well, you can take the limit as n approaches infinity of 1 over 3 plus 1 over 5 to the n. That's just how negative exponents work. But now take a look, right? 1 over 5 to the n goes to 0. Okay. So our denominator here is just 3 in limit. And what is that? Well, that's just 1/3. Okay. This is not 0. The limit. So the limit is not 0. So the sum diverges. See how easy it is to take a limit. If it's 0, you can't do much. But if it's not 0, you can say that the sum is divergent. You win. But take a look at this next one, right? Sine of n. We're summing sine of n. Think about the graph of the sine function, right? It's bounded, right? But is bounded enough? Well, the answer is no. Okay, bounded is not enough. Okay, we have the monotone convergence theorem and the bounded convergence theorems. Okay, but bounded is not enough. Okay, we note here that this limit does not exist. Okay, because it oscillates. Okay, sine oscillates. Okay, we could have even made this like, say, sine of n pi or whatever it's, or, well, really n pi over 2 perhaps. Okay, it oscillates. Okay, so what happens? Well, limit does not exist. Does not exist is definitely not 0, so the sum diverges. Okay, so if the limit doesn't exist, the sum diverges. Okay, very nice, right? I like this last one here. Well, this next one here. Log of 1 plus 2 over n. Okay, well, that's going to require some stuff. You can finagle this some ways, but we're going to go ahead and just, again, take the limit here. Okay, so we're going to take the limit of log of 1 plus 2 over n. Okay, we're going to use a fact here from analysis where I can pass limits through continuous functions. We're just going to go ahead and wave our hands at that for a second, but if you have a continuous function, you can go ahead and pass the limit through. So we're looking at the natural log of the limits. So it goes to infinity of 1 plus 2 over n. Okay, well, 2 over n goes to 0. Okay, so the inside there, that limit is just 1. Okay, well, what's the log of 1? 0. We don't know. Because the limit was 0, okay, we don't get any new information. Okay, we can't make a conclusion here. Okay, we'll soon learn of ways of determining if this guy converges or not. Okay, there are ways of doing that. All right, this last one here is pretty interesting. Log of n over n. Well, take a limit. So we take the limit here, log n over n. Oh man, well, how do we do that? Well, let's think, right? If I plugged in, I'm using bunny quotes here. If I plugged in infinity, well, I get infinity over infinity. Thinking of a surgical procedure for this limit here? L'Hopital. You have to use L'Hopital's rule, okay? So we're going to take the derivative of top and bottom here. Okay, derivative of log n is 1 over n. Derivative of n is just 1. And we know that 1 over n goes to 0. So this limit is 0. But guess what? The limit was 0. We don't know. Okay. So what do we really take away from here, okay? Let's take a look back at some of these ones that we did here, right? Okay, I take limits. Okay, if I want to see if the sum diverges or not, I just take limits. Okay, if the limit is different from zero, okay, or the limit does not exist, as we saw here, the sum diverges. But if the limit is zero, we get no new information. Okay, if the limit is zero, we get no new information. Okay. So this was just an exploration of how to use this divergence test, this nth term test, okay? It's a gut feeling, okay? It's probably one of the ones that's easiest to do, right? If you have a gut feeling that your terms will blow up, okay, or the limit does not exist for your terms, right? Well, then you can say that the sum diverges, right? Okay, think about it. For it to converge, we want to have a limit of those partial sums. Well, eventually you kind of want those numbers to be small enough quickly enough, okay? So we'll do some more examples in the next video of how to apply this divergence test. And I'll see you in the next one.